So let's continue. Welcome back to course again, tutorial 12, remote sensing indices. And with this video, we will we will continue with our remote sensing indices, and we will use the indexes related to built-up areas, urbanization indices, which are used to detect urbanization rate and urban sprawl, and also normalize different water index in order to find the water areas. So again, open the tutorial 12 remote sensing indices and create the data frame urban index. So we will use at first the most wide used urban index is normalized difference built-up index, and for this we need two bands, sphere 1 and near infrared. So image analysis do not have an option to. Let's first just drag Landsat 16 composite stacked layers to this place, and let's close this one. And also for 2020, this one. So these are 2 years. Let's create this name in Landsat 2020. So these are 2 years. So we can also just use swipe tool to see to compare them. So image analysis do not have an option to use normalized difference built-up index. Image analysis only have NDBI, but we can calculate NDBI with raster calculator. So see that actually we cannot use here this Landsat 16 and 20 composite of bands. We only can use them in image analysis to calculate NDBI. So therefore we need to calculate NDBI at first here. So using this grouped separate layers. So let's close this area. So and check this place. So I open raster calculator. So we need sphere 1 and near infrared. So sphere minus near infrared, sphere 1 plus near infrared. So sphere 1 is our 6th band, because sphere 2 is the 7th band, the last band. So at first use float tool, because this will be float values. Again, NDBI as well as NDVI has values from -1 to +1. So minus sphere 1 minus near infrared is the 5th band, right? And divide float sphere 1 plus near infrared. So both of them are float. So, and I will put here normalized difference built-up index. Normalized difference built-up index for 2016. Normalized difference built-up index for 2016, and click OK. And let's wait our results. So this is our normalized difference built-up index. I can close this areas. So this is my normalized difference built-up index. So white areas represent high level of built-up index pixels, and low areas, these are dark areas, low built-up index. So this one mostly vegetation areas, agricultural areas, and this one is my built-up index. So we can check values. So this is urban area. So this one is built up definitely. 11. It's actually not very high. So you know that it is more correct to calculate NDBI using more higher spatial resolution image like Sentinel or even higher, because Landsat has the pixel resolution of 30 to 30, which means 900 square meters, one pixel. Therefore, even if this pixel has both the real properties, buildings, asphalt, and mix it with trees and bare soil, so Landsat will mix all these energies from reflected by these land use classes into one and give something on average. So therefore, this will be not precise and accurate. So this accurate classification of urban. So these areas are actually C high. So this one has a high concentration of built-up areas, built-up index buildings. So and again, let's do the same with 2020 raster calculator. So this is my let's again use float sphere minus near infrared and float sphere plus near infrared. Normalized difference built up index 2020. So let's wait until it will calculate it. Actually, we don't need this images now. So my NDBI is calculated. I can close this images. So this is my NDBI for 2020. Almost the same results here. This is urban areas. Actually, these areas also have a high level of built up, but actually these are minerals, can be rocks, probably asphalt, and those objects, probably concrete also, those objects that have very close reflectance to urban reflectance, urban signature. So these areas have high level of reflection from short wave infrared one. So, and the last step is just move NDBI 20 and NDBI 16 to NDBI 16 to urban to this data frame. So, and we can also here compare. And both of them are from -1 to +1, and let's extract areas of our interest, the small area agglomeration. Let's drag it to this place, to our data frame, and use extract by mask tool. Let's first extract 2016 NDBI, extract 2016, and so this one is extracted. See this area, so I don't need this image anymore, and do the same with 2020, extract 2020, so we have two images for 2020 and 2016, and let's subtract from 2020. Can again use the float from 2020 to from 2016. So actually to subtract the previous year, older year, from the current year, and in this case we will just make a change detection analysis. So we can name it urban change. So this is the urban change, and let's change the color ramp from high to low. We can use this one and click in invert order. So this red colors will be high urban change. It means urbanization rate and increase of built up areas, and the green one is decrease. So we can see that actually from this image we can see that the city is not it's not having actually high urbanization rate in general. It showed that the decrease of urbanization rate in most of the areas. We can change it to make classify. Let's click here 3. So from minus this area, let's make it even smaller, close to 0. This close to 0, and also this is one close to 0. Can just put here again extra zeros, and this one is positive value, so it's above 0. It means that if we subtract it from one to another, that it means surplus of urbanization. So we can here click the red one. This one is okay, let's stay neutral, gray because no, and this one is decrease of urbanization. And now we can see that actually there is a urbanization trend in most cases. See, some areas are neutral, some areas are actually decreasing of urbanization. So what we can do now, we can reclassify in order to compare in order to assess the area of urbanization. So what we will do, we will change, we will put urban change. Why it's showing like this? Let's again click here, so it's close to 0. Should be even smaller, even smaller. Let's very small area, and this one is also small. So see, it's almost close, and this one is positive values. So negative means decrease of urbanization, neutral, almost neutralized, because it's almost, this area is very close to 0, and a little bit above 0, surplus of urbanization. Let's click OK. We can close this one. Let's choose color. At first change colors to appropriate ones. This one is red, this one is okay, gray. So, and now we can calculate the area and compare is there any urbanization trend. So how we will do it? So add at first field area, long integer, and go to field calculator. So we'll multiply count into 100 and divide it into 10,000. Means that in hectares, right? Because 1 hectare is 10,000 square meters. 900 is the area of the one Landsat pixel. Count the number of pixels. Let's click OK. So we can see that there is a decreasing of urbanization. So because this is a surplus of urbanization, this is neutral, right? no change, and this is a decrease of urbanization. So 16,000 hectares more than are decreasing, experiencing decrease of urbanization. This and 14,000 increase, but this is very rough values because it's hard to compare in the Landsat using Landsat pixel precise and accurate urbanization rate. And once again, we can also use another urbanization index. It's called urban index. Again, raster calculator. Urban index is this one, short. And now we will use the second shortwave infrared. So again, second shortwave infrared. I will close here. Go back. Raster calculator. So second is the last one. So I forgot to use the float. Minus near infrared divide float plus near infrared. This is urban index 2016. So this is my urban index 2016. So values are also from -1 to +1, and I will do the same step to 2020. So again, use the float, shortwave infrared minus near infrared, and divide to shortwave infrared plus near infrared. Urban index 2020. Click OK. This is for 2020, and let's again drag them to our data frame. 2020 urban index, and extract by mask urban index. So again, at first I should activate it, and urban, close and open again. Extract by mask, urban index, urban is the shapefile, UBI extract 2016. So this is my extracted file, urban index. So I can remove this one already and do the same with the 2020 urban UBI extract 2020. So now we can again compare urbanization rate with the raster calculator. Just let's subtract 2016 from 2020. UBI change. So according to this one index, so actually they can differ in results. So we just at first take a glance to. So actually urban index showing the same results almost, comparing to our NDBI. So we can again change the classification, 3 classes. So this value should be close to 0. So minus, so this is a negative values, this values is almost 0, and this is the positive values about 0. So I can delete 1 0 here. So this is a surplus of urbanization, right? Urbanization rate. This is gray is no change, and this is one is reduce of urbanization. And we can compare now with see, almost probably this urban change has less negative values. So let's reclassify urban change, reclassify 3 positive values. So reclass urban change, and change the colors to appropriate, red one, gray, and we can now again calculate the areas, area long integer, and repeat the same steps, multiplied 100 and divided into 10,000. So almost very close values. We can open again the urban change. Where is it? This was right? No, this one. So we can compare. This is a NDBI, right? Probably I should change the name to NDBI change, and this is a UBI change. So we can compare NDBI change into UBI change. So this NDBI change 16 hectares minus of urbanizations is 50,200. So neutral is 231. This is almost no change neutral, and surplus of urbanization almost 15,000 in UBI, and this one is 14,000 hectares. So values are actually very close to each other. So this both indexes are very reliable when you want to detect urbanization rate. So I will pause the video here, and we will continue with water index with the next video.